namely the functor Bt, which goes from nilpotent displays over R to p-divisible formal groups over R is an equivalence or anti-equivalence of equivalence, it's covariant of categories. If R is separated and complete in the p-adic topology. So this is absolutely the strongest result one can possibly expect. It solves, in particular, a conjecture of zinc made in his asterisk volume, the paper from the p-adic semester, where zinc conjectured this for any Noetherian ring in which P is nilpotent, but there's no reason to assume the ring is Noetherian. Lau uses the theory that Grothendieck told Ilussi he should develop in a letter from 1968 or 69, and that was what led to a large part of Ilussi's thesis, the deformation theory in terms of the truncated cotangent complex for so-called truncated Bossari-Tate groups. These are groups that are not necessarily the kernel of p to the n on a true p-divisible group, but behave as though they were in the sense that they are finite flat group schemes killed by p to the n with the property that's thought of as modules over the ring Z mod p to the n. They are flat. And so Lau proves it using these, and he has a notion of a truncated display. So I think this is a rather amazing result. I'm glad to be able to tell you about it. I began reading the proof last night, around midnight, but Zinc has studied it carefully and says it's okay. I certainly hope he's right. Okay. So, crystalline Dieudonné theory. That's what I want to talk about today. In particular, I want to prove the Serre-Tate theorem, and I want to talk about what's been referred to as the Grothendieck-Messing theorem, deformations. I want to also tell you about what we know about crystalline Dieudonné theory. So, we assume we have some scheme on which P is locally nilpotent, and the theory is going to be local for the Zariski topology. So if you want, P can be nilpotent. Sigma is going to stand for the spectrum, not the formal spectrum, the genuine spectrum of the ring of p-adic integers. It's equipped with a canonical divided power structure because p to the n over n factorial is always divisible by p. And we consider on the category of schemes over S, various topologies, in particular the Zariski topology, the flat FPPF topology, the FPQC topology, the étale topology, the symptomic topology. Symptomic means flat, locally complete intersection. And it's theory that Fontaine and I used extensively, and then others in working on the p-adic Hodge theory. So now we're going to denote by Chris S over sigma the category whose objects are divided power thickening. So we have U an S scheme, T a sigma scheme. We assume P is nilpotent or locally nilpotent on T. Little I is a closed immersion of U into T, and we assume on the ideal defining that closed immersion, we are given a divided power structure called gamma. Apropos of divided powers, I might... Yes, sorry. I'm very sorry. So I wanted to say, apropos of divided powers, in the axioms that are in the notes, Ching Lai and France, for their lectures, they are written down explicitly, and I want to call to your attention, since people have been giving exercises. Here's an exercise. To show that this is an integer. This can be done in various ways. If maybe if Poonen were here, he might be able to tell me that there are 40 proofs of this, but oh, okay. Thank you. Do you know many proofs of this? I think I know at least two also. One is a combinatorial proof, but I don't want to give the interpretation of this. I leave that as an exercise. And another is by expressing it as a product of binomial coefficients. But I'm sure there are more proofs of this. So this is a natural number. And I don't think that's immediate if you try to write out for each p, the p-adic digit expansion of m times m and n, and then take their product. There's a formula that for any integer n, or call it, yes, n, the p-adic valuation of n factorial is n minus the sum of its p-adic digits, that quantity in a numerator, p minus 1 in the denominator. But, okay, so that's an elementary exercise. So I return now to the category of, which is going to be what we use for the crystalline site. So morphisms are going to be commutative diagrams where F is an S morphism, G is a sigma morphism, and G commutes with divided powers. We say such a diagram is Cartesian if U prime is the fiber product of U and T prime over T, and we say the object is affine if T is an affine scheme, or equivalently if U is an affine scheme. So this is the input category for the, well, for not only for crystalline Dieudonné theory, but for crystalline cohomology as well. So going back over there, I should finish reading it. The topology is defined by giving certain diagrams of the form star, which are Cartesian, where the union of, I hope this is legible, the union of the images of the schemes T prime J under the morphisms G J is equal to T, and where first we allowed open sets for the T prime J, then we allow, depending upon the topology, if it's the Zariski topology, we only allow open sets. Then if it's the flat topology, we allow such Cartesian diagrams where T prime and T are both affine, and where the morphism from T prime to T should be flat, and the union, or faithfully flat, and that defines, or if we want, that would be FPQC. If we want FPPF, it should be faithfully flat and finitely presented. If we want étal, it should be étal, etc. So schemes over S is a category endowed with the analogous topology. We just look at coverings of S schemes, say U prime to U, which have various properties depending upon the topology. And there's an obvious inclusion map from sheaves on S with the particular topology to sheaves on this S over sigma sub tau, and that's defined in the only way you can imagine, or at least it's the only way I can imagine. If we have a sheaf on S, call it script F, have a sheaf on S over sigma, call it script G. The direct image of F evaluated on UT gamma is F of U. The inverse image of G evaluated on U is, we think of U mapping to U via the identity defined by the zero ideal, with the only possible divided power structure on the zero ideal, the trivial divided power structure. And I upper star is left adjoint to I lower star, and this is in fact a morphism of topoi. We're going to write F underline systematically for I lower star of F, and we'll be interested in F underline when, for example, F is the sheaf represented by a scheme, for example, a group scheme, for example, an abelian scheme, or, for example, a p-divisible group. So F goes to F underline is exact for the symptomic and the Zariski topology. For the FPPF topology, it is not in general exact, but it is the higher direct images are 0 if F is either a quasi-coherent sheaf or represented by a smooth commutative group scheme. And R1 F lower star of I lower star of F is 0 if F is a flat affine group scheme or a p-divisible group. So these statements are all elementary, but are used constantly in terms of setting up the homological formalism that goes into crystalline Dieudonné theory. We have particular sheaves, O, or O S over sigma, I S over sigma with a K in square brackets standing for the divided power ideal, or the kth divided power of the divided power ideal. So the sections over U, I'll just say UT and suppress saying gamma constantly, of O are just the sections over T of the structure sheaf on T. The sections over UT of this sheaf script I with the K in square brackets is you take the divided power ideal and you take its kth divided power. That is the ideal generated by, if we have elements little x1 through little xn in I, we take gamma I1 of little x1, product through gamma In of little xn for all I1, comma, etc. In, where the sum is at least k. So that's the definition of the divided power filtration on a divided power ideal. Now we're going to define the notion of a crystal. And there's going to be a basic fact that the value of the crystalline Dieudonné functor on a finite flat P group or on a p-divisible group or on an abelian scheme is a crystal. So there are non-quasi-coherent, but we're only going to look at quasi-coherent crystals today. So it's the giving of a module over this ring OS sigma such that if we look at on any particular object in the crystalline site, the Zariski sheaf defined on open sets by taking the sheaf, the sections of it to be the sections over U prime T prime of when T prime is open in T. That should be a quasi-coherent sheaf, and we further require that for any Cartesian diagram of the type star that we had before, not for any Cartesian diagram, for an arbitrary commutative diagram of the type star, we have this condition that the inverse image of MUT under G star is MU prime T prime. And later in the talk, I'm going to talk about an alternative, more concrete way of interpreting crystals under some hypotheses. So we make immediately the definition if we have a finite flat group scheme or a abelian scheme or a p-divisible group. D star of G is x1 of G underline, that is I lowest star of G, with coefficients in O, the structural sheaf for the crystalline site. So this version of Dieudonné theory is going to be contravariant. If you want a covariant theory, you apply it to D upper star of G upper star, where G upper star is the Cartier dual finite group, or the Serre dual p-divisible group, or the dual abelian scheme. Okay. And the first result we have is that this D star of G is a quasi-coherent crystal which is finitely presented, or locally finitely presented. In the case of a finite flat group, it is a locally free of rank 2G. G is the relative dimension. In the case G is an abelian scheme. And it is locally free of rank H if H is the height of the p-divisible group. So it has good properties, very good properties for abelian schemes and for p-divisible groups, and at least it is a crystal which is locally finitely presented for an arbitrary finite flat group scheme. So next, it is independent of the topology chosen. That is, we had the possibility of the Zariski, the Étale, the symptomic, the FPPF, the FPQC topology, and calculating this, it has values on the underlying categories for all of those sites is the category I initially wrote down, so it makes sense to say that it is independent of the topology. It's obviously functorial in G because the sheaf, the local X, is contravariant in G. That's obvious. It's covariant in the second variable, the one to the right of the comma. And it commutes with arbitrary base change. If we have a morphism from S prime to S, inducing corresponding morphism, call it U tilde, then U tilde upper star of D upper star of G is D upper star applied to the base change of G from S to S prime. And there's a natural mapping which is always an isomorphism. Now, if we're going to apply that functoriality in a moment when S has characteristic P, so if we take the absolute Frobenius on S and denote by upper P in parentheses the result of pulling back via that, then we have the Frobenius morphism from G to G upper P if G is any scheme on S. We have the Verschiebung morphism from G upper P to G if G is any flat commutative group scheme, or, for that matter, a p-divisible group on S. I don't know. Have people here, obviously some have you seen a construction of the Verschiebung for a flat commutative group scheme? You can find it given in the book of Dumazor-Gabriel or in SGA 3. In the case of a finite flat group scheme, it is defined as the transpose of the Frobenius. You take Frobenius on G star, the Cartier dual, and you dualize that, and you get the Verschiebung. That works also for p-divisible groups. If you apply it to abelian schemes, it works also provided you grant the existence of the dual abelian scheme, which is much deeper, particularly in the non-projective case. That is, if you have an abelian scheme which is not a projective abelian scheme, and such examples exist and were found by Raynaud in his thesis. You can find them. So, to prove the existence of the dual abelian scheme, which I have the impression has been taken for granted in some lectures here, this is a serious theorem due to Raynaud, and one can find, in my view, a too brief discussion as to why it's true in Falting's Chi, or at least, I would say it's a sketch of a proof. But in any case, the Verschiebung exists in full generality, that we want to make use of it. So, returning there, we get on D star of G these two endomorphisms, and they both composites are equal to P. By definition, this is what we call a Dieudonné crystal. That is, a quasi-coherent crystal endowed with two such endomorphisms, and where both composites are equal to P. So there's obviously an exact sequence on the crystalline site for any one of these topologies. I goes to O, the structural sheaf for the crystalline site, goes to the GA underline. GA underline really means the sheaf represented by OS when we extend it to all schemes over S. So if we have an abelian scheme or a p-divisible group, the corresponding sequence where we can put, I didn't, for some reason didn't put it, but there should be a 0 on the right. This is always an exact sequence. If we take G to be finite and flat, the D star of G to X1 GGA is still surjective, but in general there is a non-trivial kernel to the mapping from X1 of GI to D star of G. So we don't have in full generality an exact sequence, and in fact the kernel, if G is finite, the kernel of the mapping from X1 of GI to D lower star of G has a concrete interpretation in terms of what's called the Colli complex. This is the pullback along the identity section of the cotangent complex. So, but we don't need that today, and I won't discuss it today. So if we have a short exact sequence of groups which are either finite flat groups or abelian schemes or p-divisible groups, or we can mix the three, G and G prime can be, for example, abelian schemes. G prime can be finite, so G to G double prime would be an isogeny. Then we have a sequence which is always exact on the right when we pull back. In general, for finite locally free groups, D star of G double prime to D star of G is not in general injective. For abelian schemes or for p-divisible groups, it is always injective. Then we have a complement to this. So now I want to describe what a crystal is in an alternative way. So let's begin with, we have S, assume it's affine, it's spec of a ring of characteristic P, and assume the ring admits a P base. So what this means is that if we look at the mapping from R to itself given by Frobenius, then there should be a family of elements xi, I running through some index set, with the property that the monomials in the xi's, where each exponent has degree at most p minus 1, should make the R, which is the target of Frobenius, a free module with that as basis over the R, which is the source of Frobenius. So, examples of rings which admit P bases are fields. This is a classical result, which goes back to maybe Hensel. I mean, certainly more than close to 100 years ago. If we have a ring which is of finite, a ring which admits a P basis, and a smooth ring over, if R is smooth over a ring admitting a P base, or is smooth over a field, or is a power series infinitely many variables over a ring admitting a P base, these rings all admit a P base. And for such rings, we can give a much more concrete description of what a crystal is. So given such an R admitting a P base, there is then a flat, p-adically separated and complete ZP algebra, unique up to non-canonical isomorphism, so to speak, depending upon it will be canonical if the cardinality of the P base is 0. And an isomorphism, we call this ring R infinity. So R infinity is a lifting of R from, so to speak, FP to the p-adic integers. So if we choose a P base for R and any elements lifting the P base in R infinity, then to give a quasi-coherent crystal on spec of R is the same as giving a module on this R infinity of the following type. So the module should be p-adically separated and complete, called the module M, and it should admit ZP linear endomorphisms which commute, indexed by the index set for the P base. The nabla I of little m should be 0 for almost all I, this depending upon little m for each little m. Nabla I of R times m should be R times nabla I of m plus the partial derivative with respect to x tilde I of R applied to m. In other words, this is covariant differentiation in the direction corresponding to xi tilde. And this is this derivation is the unique continuous derivation of R infinity, satisfying that applied to x tilde j, it is the Kronecker delta ij. And finally, the last condition, this is the so-called quasi-nilpotence condition, that for each I there should exist an ni with the property that nabla I to the ni applied to m should be contained in p times m. Okay. And it's that quasi-nilpotence condition which allows one to, if we have a divided power thickening, write down a Taylor series expansion to relate this definition or this description of a crystal to the one given earlier. Just 1 second. If a P base is empty, yes, this means that R is a perfect ring, and then a P base will be, or rather R infinity will just be the Witt vectors of R. Yes, thank you. So, So I want to now give examples of crystals. This should be a D star. I wrote it, I left out the star, excuse me. If we have an étale group, finite or p-divisible, and we take its Pontryagin dual in the sense of Hom into QP mod ZP, we could write Hom into the circle, but that would be a little perverse in this context, but it would be the same. Then, it was remarked earlier, if we have something étale, if we have U contained in T defined by a nil ideal, then étale sheaves on U and étale sheaves or étale schemes on U and étale schemes on T, these categories are equivalent. That is, anything étale over U extends uniquely to something étale over T. So that if we, given the étale group, if we denote by G upper U its pullback, which is also to U, which is also étale, and take its Pontryagin dual and take its unique lifting to T, then the value of the Dieudonné crystal, again, that should have a star. I apologize, it's contravariant. We take this Pontryagin dual of GT tensor over the p-adic integers with OT. And similarly, if G is of multiplicative type, which by definition means its dual is étale, then the value of the crystal is the Cartier dual, which again, by the same equivalence, if G is of multiplicative type, it lifts uniquely to T, so we denote that by G sub T. We take its Cartier dual, and we tensor that over ZP with OT. So for either étale or multiplicative type groups, these crystals are as naive as possible. Yeah. Excuse me? It's a finite group scheme if G is finite and flat and étale. It's a finite étale group. And if G is a p-divisible group, then it is, if you want to give a p-divisible group or to give its Tate module is the same thing. And I want to think of it as having the Pontryagin dual Tate module. So it would be a representation of the Galois group or the fundamental group, a continuous representation, and you could then take the dual representation. Assume that S is a scheme of characteristic P, then the ideal of, assume further that T, the nilpotent thickening, has characteristic P. Then if we have an element in the kernel of the mapping from OT to OU, its pth power is P factorial times its pth divided power, and since T has characteristic P, this is 0. And this permits us to define a mapping of schemes from T back to U, making that diagram commute. Now, if the group G is killed by F or V, this means it's not an abelian scheme unless it's the trivial abelian scheme, and it's not a p-divisible group unless it's the trivial p-divisible group. So it's a finite group. Then the crystal and again, it should be D upper star, I apologize again, evaluated on the scheme of characteristic P is, for the group killed by F, we take the cotangent space at the identity and pull it back to T by this mapping phi. If the group is killed by V, we take phi upper star of the Lie algebra of the Cartier dual. So at least for these groups killed by F or V, we do have a concrete description of... Excuse me? Yes, I'm sorry. Okay. So now I want to talk about the relationship between crystalline Dieudonné theory before I discuss properties of the serious properties of the crystalline Dieudonné functor and so-called classical Dieudonné theory. So classical Dieudonné theory was, in Qinglai's lecture this morning, taken as a black box. I want to make it more explicit, but I'm going to talk about the contravariant theory. If you prefer the covariant theory, you take the contravariant theory and apply it to the dual group. So for any commutative ring whatsoever, any Z algebra, call it A, there's a notion of the Witt covectors. If A was Z mod P, then the Witt covectors of A would be QP modulo ZP. But it makes sense for any ring A, and here we take infinite vectors, but indexed by the non-positive integers, A0, A minus 1, and so on, moving to the back, moving towards minus infinity, and we only look at those with the following property, that for each A, each vector of that form, there should be an integer r such that the ideal generated by the tail part, sufficiently negative tail part, is a nilpotent ideal. Then if we take the polynomials defining Witt vector addition, Sm, depending upon the two m variables, x is x0 through xm, y0 through ym, and for two covectors, we can define their sum, which will be a new covector. We take the sequence which is written there, we take the mth Witt polynomial, apply it beginning for any n whatsoever. Say n equals minus 13, or n equals 13. We take Sm, take m to be 44. So we have going from A minus 57 up to A minus 13, comma B minus 57 to B minus 13. And now we let m go to plus infinity. Then if we call that element, that sequence is eventually constant because of the nilpotence hypothesis on the ideals, the A's with tails sufficiently negative and the B's. And we take C sub n to be the limit of that sequence, and then the vector consisting of the C sub minus n's is indeed a covector, and this defines a commutative group structure. So this idea was first developed by Bassati in the late 1950s, early 1960s. It was in a slightly different way, the way I'm giving now, done by Fontaine in his asterisk volume in the late 1970s, and one can find many exercises on Witt vectors, the lambda of this morning's lecture, etc., in Bourbaki, Algèbre commutative, chapitre 9, paragraph 1. So there are something like 60 exercises devoted to Witt vectors, covectors, universal lambda ring, etc. They are well worth doing. Okay, now we assume that we have a perfect field of characteristic P, and G is a finite flat or finite group or a p-divisible group. We consider the covectors as a functor on k, little k algebras. Then this CW of A for A at K algebra is equipped with a structure of module over the Witt vectors of K. And this is done explicitly in a way that I'll tell you. And you'll see here that we use, in a strong way, the fact that K is a perfect field. This would break down entirely if K was not perfect. But if we have a Witt vector, I'll call it alpha arrow, and we have a covector, A arrow, then the minus nth component of this alpha times n, the scalar multiple, we take, just as before, a limit as m goes to infinity, but we take the pm, these are the polynomials defining Witt vector multiplication. And notice that for the alpha, we take p to the n plus m roots of the alpha 0 through alpha m. And this defines a structure of a W of K module on CW of A, functorial in A. Frobenius on CW of A is defined by raising each coordinate to the pth power. Verschiebung is defined by shifting to the right. And the usual relations are satisfied, and this becomes a module over the ring this morning, which was denoted, I believe, by R sub k, R sub little k in this case, it would be. Okay. And we have the next, top of the next transparency just indicates that fact, that F times V equals V times F equals P. Capital F is little f semilinear. Capital V is little f inverse semilinear. Little f was called sigma this morning. Now, the classical Dieudonné module is defined by m of g is ham of g into CW. We think of g as a functor on commutative K algebra. CW is a functor on commutative K algebras. And this is the Dieudonné module that one finds discussed and properties proved in Fontaine's asterisk volume. Now, I want to relate this to the crystalline Dieudonné module. Notice m of g is contravariant in g, of course. So there is a short exact sequence, an extension of CW underline by OS over sigma. I don't need and I don't want to describe what the middle term is explicitly. Its construction uses the divided powers. But taking the co-boundary map in the low terms of the cohomology sequence, or the sequence of extensions, we find a mapping from the local Ham, from G underline to CW underline, goes to the X1 of G with coefficients in O. That is our D star. Now, if we let not bold D, but D, straight D, ordinary D, be the global sections on the structural sheaf. So here, because K is a perfect field, this is just the projective limit of the sections on spec of Wn of K. It gives us a map taking global sections from M of G to D of G, and this is an F semilinear isomorphism. In other words, classical Dieudonné theory and crystalline Dieudonné theory are completely equivalent when we're working over a perfect field. So in particular, by the result that was mentioned this morning, for either finite flat or for p-divisible groups, the crystalline Dieudonné functor is, because the classical one is, an equivalence of categories. So now I want to look a little more and relate we have a multiplicative sequence where we have quotient GM O star, the invertible elements in O, and we have 1 plus the ideal. And now, divided powers enable us to take the logarithm always of 1 plus x, so it's given by the usual logarithm series, where we write x to the n over n as being n minus 1 factorial times the nth divided power of x. And that logarithm is a homomorphism from the multiplicative group 1 plus I, because every section of I is locally nilpotent, 1 plus I is a group, to I, and this enables us to push out the extension written up there, or in fancy terms, gives us a morphism in the derived category from GM underlined to O shifted, O placed in degree minus 1. So I apologize for this derived category business, but it's 2006. So we apply the R-harm, and we then truncate in degree less than or equal to 1 to get a mapping from this G star underline, which I call alpha, to, I'll tell you, delta G of 1. Delta G is R-harm of G into O, that complex truncated at less than or equal to 1, so it has two terms, and it is a perfect complex if it is just d of G placed in degree 1, because harm of G into O is 0 if G is p divisible, or in a abelian scheme, if G is finite, it has a term in degree 0, a term in degree 1, and the 1 in square brackets means we shift that complex to the left so as to place its two non-zero terms in degree minus 1 and degree 0. So again, I apologize for the derived category, but if you want, it's unnecessary if you want to stick to p divisible or abelian schemes, but if you want finite groups, it's absolutely necessary. So we transpose, that is, we take the R-harm of that morphism, the one called alpha, into the O S over sigma, and we get a morphism in the derived category, which becomes much simpler if we're dealing with a p-divisible group or an abelian scheme. Then it would be a mapping, for, say, for a p-divisible group or an abelian scheme from d of G, check, the linear dual, to d of G star, the Serre dual or the Picard scheme, pick 0. For a finite group, I repeat here what I said, what the definition of this delta of G, this is the so-called Dieudonné complex associated to the finite group. So if we notice in particular that the alpha gives us a mapping from G star to D star of G. If G is a p-divisible group, there is an extension of G star by D star of G that I'll describe explicitly on the next transparency. So it's obtained as follows. We take the comma sequence for G star. We push out. We assume we'd have an object on the crystalline site where T is killed by P to the n. We push out along the homomorphism from G star n to D G star n, and we use the fact that on the object killed by P to the n, D star for the full P divisible group and D star of the kernel of P to the n, these are the same. And in this way, we obtain the extension that is written here on the lowest line. only over here, there's a misprint where I say push out along G star to the n, kernel of P to the n on G star. It should be D star of G n. So that's a misprint. On the target, the star inside parentheses is wrong. So now the co-boundary mapping gives us the homomorphism from the dual in the sense of linear algebra to the Dieudonné crystal for the dual group. And we have our second theorem that for G finite, the phi G is a quasi-isomorphism, an isomorphism in the derived category. And for G P divisible, or an abelian scheme, it's just an isomorphism between the linear algebra dual and D star applied to the Serre dual of the P divisible group. So classically, the duality between Dieudonné module for a group and Dieudonné module for its dual was established using the Artin-Hasse exponential. In my opinion, this method is at least conceptually clearer. It's different. Okay, now I want to discuss faithfulness properties of D star. These are the main theorems. So we assume S has characteristic P. And the first thing is that D star is, because it's contravariant, it's an anti-equivalence of categories between finite étale or finite multiplicative type groups and Dieudonné crystals locally killed by a power of P such that F, or respectively V, is an isomorphism. So this is an elementary fact. This is not one of the serious theorems at all. But it's useful. So if we have a P divisible group, set at the bottom there, so this is the same as a least p-adic sheaf, an étale P divisible group is the same as a least p-adic sheaf on S. These are equivalent then to so-called unit root F crystals on S. Okay, so then there's a theorem that Berthelot and I proved in our paper in the Growth and Festschrift. If we have a locally Noetherian and regular scheme, then the functor D star is fully faithful both for finite flat groups and for P divisible groups. We use the Néron-Popescu desingularization to reduce to the case where S admits locally a P base. Because if we have an algebra which is regular, say a local ring which is regular, it is formally smooth over Fp and consequently can be written as a filtered inductive limit of smooth algebras over Fp. That's a very serious theorem. But then, modulo that, the proof is really written down in detail in our paper in the Growth and Festschrift. Yes, Popescu's theorem says that if we have a regular local ring, I mean, it's more general, but we have a regular local ring which is formally smooth over a field, any field, then that ring, it doesn't have to be a local ring. We have a regular ring, meaning it's Noetherian in all its localizations, or regular local rings, and it is formally smooth over a field. Then it is a filtered inductive limit of smooth algebras over that field. So it frequently enables one to reduce statements about regular rings If the field was of characteristic 0, a regular ring would be a smooth ring. A regular ring of finite type would be over the field would necessarily be smooth, but that's not true in characteristic P. But the theorem is published by Popescu in Kyoto Journal in 1985, but lots of people have lots of problems understanding his proofs. But Swan, in about 1995 or 1996, wrote down a set of notes where he gave a very detailed and convincing proof. Okay. There's some bad news with regard to the Dieudonné functor. It is not faithful for groups over the following explicit ring. We take polynomials in 6 variables, mod out by the pth powers of the 6 variables, and then take x1, x2, plus x3, x4, plus x5, x6. K is a field of characteristic P. Algebraically closed field, any field of characteristic P. So this ring is not a complete intersection, and that's what causes the problem. It is not fully faithful on a ring as simple as polynomials in 1 variable over a perfect field modulo x to the p. So on such nilpotent rings, it is not fully faithful. So now we ask, when is D star going to be an equivalence of categories? Not much is known for finite groups, but for p-divisible groups, quite a bit is known. So Bloch in 1974, in a non-published manuscript, established it for S smooth over a perfect field, provided one assumes that the group is connected, in other words, is a p-divisible formal group. And in his proof, he makes extensive use both of the crystalline Dieudonné theory, as it was developed at that time, and of the Cartier theory that was talked about briefly by me, but more extensively by Qing Lai this morning. And here, the target category is those Dieudonné crystals where F is topologically nilpotent. If we were dealing with the covariant theory discussed this morning, V would be topologically nilpotent. Then Kato in the early 90s extended to all p-divisible groups for S smooth over a perfect field of characteristic 3 or more, the equivalence. And then I, using de Jong's thesis, or a portion of de Jong's thesis, his paper in Inventiones on crystalline Dieudonné theory for finite groups, extended Kato's result to also include the case P equals 2 as well. Now, Kato's proof has never been published. My proof of the characteristic 2 has never been published because, we have better results now. Also because of, at least in my case, indolence. And I apologize for that. Excuse me? Yes, absolutely. I'm coming to that now. So, in de Jong's thesis, he gives an equivalence of categories between p-divisible groups over a scheme S of the form R mod P to the R, where R is a flat WK algebra, K is a perfect field, and R has the following form. It's a power series, quotient of a power series ring by an ideal I. He gives himself an endomorphism, sigma, which lifts the Frobenius, and there's a technical condition imposed on the pair R and sigma. This is, Franz knows, U bar and gamma bar should be nilpotent, is Johann's technical condition. And then p-divisible groups over the spectrum of R mod P and the category of finitely generated free R modules together with a sigma linear mapping F, a mapping it can't be sigma inverse, but V from M to the Frobenius transpose. So the M up a sigma means base change via Frobenius. F times V equals V times F equals multiplication by P. Such modules are equivalent to P divisible groups over R mod P. This is the, I think, so to speak, the final theorem in this paper of de Young's. Then there are better results. So let me say, in particular, this technical condition is satisfied if I is generated by monomials, or if R mod P is reduced and the sigma of xi, the variables, have no linear or constant terms. So they are of degree greater than or equal to 2. And the proof is really based upon crystalline Dieudonné theory in an essential way. But then we come to de Young's paper in the IHES journal from 1995. If S is smooth over a field having a finite P basis, then D star from the P divisible groups on S to locally free Dieudonné crystals, this is always an equivalence of categories. So the advantage over Kato's non-published result is, first of all, this is published, and second of all, the field is no longer required to be perfect. It can have a finite P basis. And fields which have infinite P bases, and in Nagata's book on local rings, he makes extensive use of such fields for making various counterexamples. Then there's a second theorem, which was in de Young's 1995 paper, and then in my paper with him from 1999, extended slightly. So S is any scheme of finite type over a field, and you take P divisible groups up to isogeny over S, and F isocrystals, that is, you make P invertible, then this functor is fully faithful. In de Young's Blue Journal paper, this was proved again where S has a finite P, where K has a finite P basis, the field, and in my paper with Johann, it was extended arbitrary P basis. Then we have in our paper another theorem. If S is an excellent scheme, all of whose local rings are complete intersections, then D star is fully faithful on the category of P divisible groups. Now, if we go back to a previous theorem, you might ask what the difference is between this theorem and the theorem, I hope I can find it rapidly, the theorem that Berthelot and I proved. I don't seem to be able to find it, so I'll just remind you. That was the theorem that said that if S is Noetherian, regular, then D star is fully faithful both for finite flat groups and for P divisible groups. So S was Noetherian and regular. Here S is an excellent scheme, so certainly Noetherian or locally Noetherian, all of whose local rings are complete intersections. So the difference is neither theorem encompasses the other. Certainly being a complete intersection means the quotient, your completion, your local ring is completed is the quotient of a regular local ring. But the difference is that in characteristic P there are discrete valuation rings, which are certainly regular rings, which are not excellent. First examples due to Nagata, and one can find in the book of Matsumura, essentially in the last 3 or 4 pages, an explicit example. So neither theorem encompasses the other. Then again, de Young and I have a proposition, I won't call it a theorem, we have a locally Noetherian and all its local rings are complete intersections. Then the functor is faithful at least on finite groups. No, absolutely not. It's going back to Dieudonné crystals. No, thank you. The question was, in the last two results where we're not taking p-divisible groups up to isogeny, what is the target category? And the answer is Dieudonné crystals. Okay, now I want to talk about the deformation theory for p-divisible groups and Certet theorem. So there's a definition of what a nilpotent divided power thickening is, and it can be weakened in various ways, but we take it to be that the ideal, the nth divided power ideal, defined explicitly there, is 0 for n sufficiently large. So if we have S a scheme on which P is nilpotent, G a p-divisible group, and a quasi-coherent OS module, which we view as a sheaf for the flat topology, by pulling back to get its sections over an S scheme T, we just pull back the ordinary quasi-coherent module to T and take its global sections on T. Then the first thing is that the homomorphisms from the p-divisible group to this sheaf is 0 because M is locally killed by a power of P and G is p-divisible. X1 is a representable functor, and it's represented by the cotangent space to the dual p-divisible group. So since I'm going to use this, I'll say something about how one establishes the so-called universal extension. So let me write this on the blackboard. So if we have, say, H over S, which is finite and flat, we have H star, the Cartier dual, which was described, I think it was in Franz's talk, as local Hom of H into GM. Then we can look, first of all, there's a natural mapping from H to Hom of H star into GM, the obvious mapping. If we have little h in H, so a t-valued point, we take chi sub H applied to an element in H star, call it U, is U of H. And since U is a homomorphism from H to GM, U of H is an element in GM, so this defines a homomorphism chi. Now, if we have a morphism from H star to GM, inside H star we have the first infinitesimal neighborhood of the unit section. So this is, we take O for H star, modulo, if I write eta for the augmentation, so we take O for H star, modulo the kernel of eta squared, and spectrum of that is this first infinitesimal neighborhood of the unit. Any homomorphism is a pointed map, so this is a pointed scheme as well. Here's the pointing. We can restrict elements in here by restriction goes to Hom pointed maps from this inf1 of H star into GM, and the pointed maps from here into GM, that's the same as giving an element in this ring which augments to 1, so in other words, of the form 1 plus something in the kernel modulo the kernel squared. So we can identify such pointed maps with the translation invariant differentials on H star. So this gives us a canonical mapping from H to here. And now call it alpha, that composite. It is an easy exercise to show that for any mapping from H to a quasi-coherent module M, there exists one and only one linear map. I emphasize, if we're in non-zero characteristic, that between vector groups there are maps like Frobenius, which are not linear, but this is linear, making the diagram commute. So this is how we get the A universal map. And now to build the universal extension, one proceeds as follows. One takes the sequence, the Kuma sequence, and one takes the mapping alpha to omega gn star. So let's work on some scheme T where p to the n times OT equals 0. Let's call it S better. And we have this alpha just constructed, and we can push out this sequence. And that gives us a sequence like this. And it is, again, an easy exercise to show that given any extension of G by something quasi-coherent, it arises uniquely by pushing out via a linear map from this term to that quasi-coherent module. So this is the construction of the universal extension. I hope I can somehow get this down because I want to go back to transparencies. Thank you. Thanks very much. Okay. So this was a digression, not in the notes. But now I summarized that discussion for that indication on the construction. So there is an extension, the universal extension, such that given any extension where M is quasi-coherent, we obtain it pushing out along a unique linear map. If A is an abelian scheme and G is the p-divisible group associated with pick 0, the dual abelian scheme, then the tangent space sequence associated to that sequence is the Hodge filtration. So in other words, if we take the universal extension for the p-divisible group associated to the dual abelian scheme, we simply get the Hodge filtration on the H1 Durham of A. Yes, I'm sorry. There should be a 0 which is not visible at the end. The mapping with target H1 of OA is, that mapping is surjective. So we have the logarithm. I recalled it a few minutes ago. And if the divided powers are nilpotent, we have its inverse, the exponential, given by gamma n of x is morally x to the n over n factorial, so we write down this series. Now, let's consider a p-divisible group on a scheme S0 and two liftings of it to an S where S is a nilpotent divided power thickening of S0. It's a consequence of Illusi's thesis, and it's certainly easier in the case of abelian schemes, that liftings always exist. And now we consider the universal extension of G1 and G2. G1 and G2 are liftings of G0. We take on the corresponding vector groups any linear mapping which lifts the mapping which is the identity. So W reduces on S0 to the identity, and we would like to fill this in so as to have a commutative diagram, but this is in general not at all possible, because if we had a commutative diagram, it would define, by passing to the quotient, a mapping from G1 to G2, lifting the identity, and such a map would be an isomorphism. But if we have, for example, the ring is Z mod P, that's the S0, or spectrum of Z mod P, and we take Z mod P squared, and we take mu P infinity cross QP mod ZP, there are going to be exactly P non-isomorphic P-divisible groups lifting mu P infinity cross QP mod ZP. So there's no possibility of having a commutative diagram in that picture there. What can we do if we can't have a commutative diagram? We can hope to specify or characterize some preferred mapping from EG1 to EG2, which in fact will be an isomorphism. So I want to describe how to do that, and that's the so-called theory of the exponential. So the top of this transparency repeats what I just said about the non-unicity of liftings. So we take the difference on that diagram. We have I1, one inclusion, I2, the other. So we take V composed with I1 minus I2 composed with W, and we call that D for difference. So there's a theorem that says that there is a unique choice of V such that for any choice of W, any linear lifting of the identity, D is an exponential. So I have to explain what that means. But first let me say, if I have more generally not the identity but a homomorphism from P-divisible groups on S0 and inducing a map on the universal extensions, and I have P-divisible groups, G and H, lifting G0 and H0, and I take any linear lift of the map from V of G0 to V of H0. Then there is a unique lift, call it little v again, from EG to EH, such that the obvious difference is an exponential. So what do I mean by an exponential? I'm going to not discuss this in detail because I have 10 minutes left and I still have more to say. I want to talk about it in a special case. So take a smooth commutative, an affine group scheme, and assume that its tangent space at the identity is locally free of finite type over some ring R, over some ring A. We call the kernel I and assume it has nilpotent divided powers. So I want to tell you what the exponential is. So it's a mapping which goes from the ring A, it's an A linear mapping, it's really a mapping from the additive group GA, which is linear, to I tensor Lie of K, to the kernel of the homomorphism, the map from homomorphisms from the additive group to K to homomorphisms from the additive group to K0. That's reduction modulo the ideal I. So if we have theta, a mapping from A to I tensor the Lie algebra, and we take theta of 1 and we write it explicitly as little I sub j tensor dj, where d1 through dm is a basis for the Lie algebra, thought of as translation invariant alinear derivations, because K is commutative, these I don't have to specify right or left, translation invariant. These derivations commute because the bracket product on the Lie bracket is 0 because the group is commutative. Take for eta the augmentation map from B, K is spec of B, to A, and define the exponential. We have to define the corresponding algebra map. It's really a map of bi-algebras, excuse me. And since we're looking at maps from GA to spec of B, this corresponds to maps from B to A of T. And explicitly, it's given by, we take little b and b, we take a sum using the nilpotence of the divided powers and the fact that the DJs commute. We can make sense of the nth divided power of ij times d of bj in the Lie algebra. We take its nth divided power, we apply it to the element b, little b, and then we take the augmentation, and that's the coefficient of t to the n. So it's called the exponential because gamma n is morally something to the nth power, so a differential operator divided by n factorial. So this is an explicit definition of the exponential, at least in this case. And now I can tell you what it means to be an exponential in the sense of the preceding slide. It means that if we look at going back to, I hope I can easily find it, yeah. This difference, the little d, to be an exponential means that we get it by applying the procedure just indicated to a linear mapping. So here I'll review again the procedure. So this characterizes certain mappings reducing to the identity as being so-called exponentials. And the theorem says that there is an unique exponential, a unique mapping such that the difference is an exponential. The unicity implies that it is an isomorphism if the mapping from G0 to H0 is an isomorphism, in particular if it's the identity, and this allows us to construct a crystal in ind-representable commutative group schemes on the nilpotent crystalline site, that is, or only look at divided power thickenings which are nilpotent, by taking G to be any lift of G0 and using the canonical isomorphism just described to get it. And then we define D of G0. This is covariant, so I don't put a star, certainly not an upper star. This is Lie of this E of G determined up to canonical isomorphism. Okay, so now I want to talk about the deformation theory. We say a submodule of the value, that is, of this covariant crystal on S, S0 included in S is a nilpotent divided power thickening, if it is such that the quotient is locally free, which implies that V is locally free, and that sequence written there lifts the tangent space sequence for the universal extension. So an admissible filtration is a submodule lifting such that the corresponding sequence has locally free quotient and it lifts the Hodge filtration. So we now consider the following category. We have pairs consisting of a p-divisible group on S0 and an admissible filtration on the value of this crystal on the thickening S0 contained in S, where it's a nilpotent thickening. And morphisms are pairs consisting of a morphism of p-divisible groups on S0, such that the induced map on crystals takes the admissible filtration for G0 to the admissible filtration for H0. So there's an obvious functor which goes from p-divisible groups over S to this category of pairs. We restrict the p-divisible group on S to S0, and we take the corresponding VG. And the deformation theorem, this Grothendieck-Messing theorem, says that this functor is an equivalence of categories. So I want to briefly say how this is proven. So we take some inductive limit of flat affine S-group schemes. And we assume that the Lie algebra, call them En, is locally free and the sequence of Lie algebras stabilizes. So, for example, this will be true in the case of the universal extension always. And here I say En, we take the universal extension, we take the inverse image of the kernel of p to the n to be En. Take a group scheme on S and a homomorphism from its restriction to S0, F0 to E0. Assume that homomorphism is a monomorphism, and assume that F is a vector group. Now we say two liftings, call that mapping U0. U and U prime are linearly compatible provided the difference between them, which is a map from in the kernel of Hom Fe to Hom F0 E0, is an exponential. So in other words, there exists a linear mapping from F to I tensor Lie algebra, or I times Lie algebra of E, such that the exponential of theta is U minus U prime. So this is a definition of what we call linear compatibility between such liftings of a given monomorphism. Now, denote by H0 the image of the U0. And any U which lifts U0 is automatically a monomorphism. So if we take H to be the image of U, it inherits by transport of structure, the structure of a vector group. Conversely, if we have a vector group lifting H0, there is a U taking F to E such that image of U equals H and U lifts U0. And U is determined up to an automorphism of F inducing the identity on F0. And two such U's, U and U prime, are automatically linearly compatible. So let H be a sub-vector group of the Lie of E, lifting Lie of H0. And now the key proposition is the following. In each linear equivalence class, that means the difference between any two should be an exponential, of liftings of U0 to monomorphisms from F to E, there is exactly one U with the property that its image is H, and then we have Lie of H is the given sub-vector group of Lie of E. So there is exactly one such U, well-defined up to an exponential. Okay, and this is the key for proving the deformation theorem. So let me explain, just with regard to the deformation theorem, the essential surjectivity of the functor. So we take some admissible filtration. We take E to be the value of the crystal, bold E. Then there will be and unique u from the vector group F to this E unique within its linear equivalence class such that its image is H and Li of H contained in the D of G0 is the given V. So now we consider for that unique U with image H, G, which is this E modulo H, the image of U. The claim is that G is itself a p-divisible group. This is not hard to show. It certainly lifts by construction G0. The fact that it is p torsion is very easy to show. The fact that multiplication by p on it is an epimorphism in the sheaf theoretic sense is not hard. The hardest part is to show that the kernel of p to the n is finite and locally free, and this requires using the exponential a little bit, but also a willingness to quote liberally from Dumazor-Gabriel, EGA4 and SGA3. But if one is willing, these are good published references, one obtains the theorem. Okay, so let me indicate now how briefly, I'm sorry to run a little over, how one will get from this the Serre-Tate theorem. So just as for, and historically, long predating the existence of the universal extension for a p-divisible group, it goes back to Rosenlicht in 1958, perhaps, the existence of a universal extension for an abelian variety. Rosenlicht didn't write about abelian schemes, but the proof is essentially the same, given given what's written in EGA3 and the coherent cohomological properties of abelian schemes. So the universal extension of an abelian scheme exists over any base. If we're on a base killed by a power of p, then the Kumma sequence pushed out in exactly the same way gives it. And now the equivalence statement for p-divisible groups, the same proof works for abelian schemes, and what is easier here is to show that the E modulo the H is in fact an abelian scheme. That's more elementary than to show the E modulo the H in the p-divisible group case is a p-divisible group. So because the kernel of P if G is the p-divisible group associated to A, then G of n, the kernel of P, on G, and the kernel of P to the n on G, and the kernel of P to the n on A are obviously the same. So since the push-out diagram is the same over there and for p-divisible groups, we get an obvious diagram like this, a mapping from E of G to E of A. Now, if A prime is a second lifting of A0 and G prime its p-divisible group, there's an analogous mapping for A prime. And now the theory of the exponential applies, so we have canonical isomorphisms. The upper one is the one discussed using the exponential. The lower one is discussed because we have a theory of the exponential for abelian schemes as well, universal extensions of abelian schemes. So how do we get Serre-Tate from this? So the claim is that in the notation that is, I'll raise this so it's visible, I'm sorry. In the notation that is on that transparency, that we have a commutative diagram involving the phis and the taus. And the proof that that claim is valid is given as follows. So if you look at how EG is constructed by pushing out the Kumma sequence, to show that the left-hand side and the right-hand side agree on EG, you have to show that their restriction to the vector group and to G in the Kuma diagram, which is where? I'm sorry. I mean, I have the right thing, but that should be that they have to agree on that explicit push-out. So we have to show it agrees on VA and on G. For G, this is easy because their difference lies in the kernel of this mapping, and since the kernel is killed by P to the N, the restriction of the difference, lift this. So the point is that the kernel of this mapping is killed by P to the N, and G is P divisible. So the restrictions to G have to be equal. For the restrictions of the difference to the vector group, one needs the exponential, and I certainly don't want to discuss in detail why that's true, but it's certainly takes half a page in my thesis to prove that. Okay, so let me conclude by explaining how from this compatibility we get the Serre-Tate theorem. So we have the functor from abelian schemes to crystals and groups on the nilpotent site. We have, taking the tangent space, the Dieudonné crystal. And as I said, I'm just repeating what I said earlier, the functor from abelian schemes on S to abelian schemes on S0 plus the admissible filtrations with the same proof, this is an equivalence of categories. So now, to go further, we have to first remind you of the formulation of the Serre-Tate and then explain how to prove it. So here's the corollary, the Serre-Tate theorem. So we go for the functor which goes from an abelian scheme on S to an abelian scheme on S0, comma, the ordinate is the P divisible group of the abelian scheme on S. So A0 is an abelian scheme on S0. G is a P divisible group on S. And this functor is an equivalence of categories between the category of abelian schemes on S and the category of abelian schemes on S0, together with a lifting of its P divisible group from S0 to S. That's the statement of Serre-Tate. Okay. So how is this proven? So we assume S is affine because it's obviously a local question. We have a nilpotent, so I should have said S0 and S, they differ. Well, it was said in Ching Li's lecture that it's a nilpotent inclusion, not necessarily with divided powers at all, but we filter it so as to have square zero ideals, and then we put trivial and therefore nilpotent divided powers on each. So we're going to prove the theorem. It suffices by induction to go step by step and prove it for a square zero ideal, which then will have, or we can give it divided powers, which are nilpotent. So the point is that the functor that I called lambda from P divisible groups on S to pairs P divisible group on S0 and admissible filtration, and the functor lambda prime from abelian schemes on S to abelian schemes on S0 and admissible filtrations. These are both equivalences of categories, and the fact that the admissible filtrations, because we can identify the crystal's value, canonically, we can identify also the admissible filtrations. From this, it follows purely formally that certate is true. Okay, so maybe, I don't know whether I should go on. The last thing I wanted to do was to relate. I have two more transparencies, so if you'll allow me 2 minutes, I'll go rapidly. I want to relate this. How do I describe in terms of the crystalline site the universal extension? So that's what I'll try to do very, very rapidly now. So we have the sequence, I'm sorry, it's not visible. The multiplicative sequence, 1 plus I goes to O star goes to GM underline. And for G of P divisible group, we can look at Hom of the kernel of P to the n into that sequence. And if we look at multiplication for m at least n, multiplication by P to the m minus n, which is an epimorphism from Gm to Gn, it induces in the other direction, because Hom is contravariant in the first variable, an inductive system of sequences of which we take the direct limit. And the first thing we prove is that the mapping on the right, the pi, is an epimorphism, so that we get an exact sequence. So on the small FPPF site, that means we only consider morphisms from T to S, which are flat and locally finitely presented. We get an exact sequence. Omega G goes to the middle terms, goes to the Hom, goes to G star, goes to 0. And what this follows from was a result I stated earlier, that the translation invariant differentials on the P divisible group can be identified with the X1 of G with values in I. And since we're on the nilpotent site, the logarithm is an isomorphism from, well, let me write it this way. We have the co-boundary mapping from Hom GM into I into X1 G into I is an isomorphism because we're assuming P to the n kills S. And then the Hom of Gn into I, 1 plus I, can be identified with Hom of Gn into I because log is an isomorphism. And this gives us the sequence that is written right there. The omega goes to the inductive limit, goes to G star. And now the final thing to say is that well, it has two components. This sequence is canonically identified with the universal extension of the dual P divisible group, G star. And the last thing is the crystalline formalism. The crystalline, as discussed at the beginning, gives us a mapping. If I have two liftings to a nilpotent thickening, G1 and G2 of G, I get two mappings between the corresponding universal extensions. And there was the mapping, the isomorphism, given by the theory of the exponential. And there's a theorem that says that these two canonical isomorphisms are, in fact, the same isomorphism. And that's a non-trivial result. And it took me essentially a full year to prove it. But I was at a conference in Rome in early June of 1972, and after having a nice dinner and getting ready for bed, brushing my teeth, just like Henri Poincaré on the bus, I had this insight, and I saw how to prove it. So thank you for your indulgence.